And then I'm going to talk about like the 5 top metrics you need to use to monitor our brokers. The key metrics when trying to figure out why are your clients slower than what you'd want them to be. Like we all have high expectations. Everyone tells us Kafka can do millions of events per second. If you don't quite see it, we have tips on how to troubleshoot. And then in case those key metrics don't tell you the whole story, Xavier will tell you how to use flame graphs to get every single detail of where clients are spending their time. So that way you are bound to find the problem and be able to fix it. So yeah, with that, let's get started. So I'm Gwen Shapira, and this is Xavier Lot. And we've been working together at Confluent pretty much forever. And for the last at least 2 years, I'm thinking we started working together on monitoring Kafka exactly 2 years ago in July 2017. And it's been a journey. We built on-prem monitoring product. We moved to monitor our cloud system. And so far, things are going amazing. This talk just keeps rebuilding itself every few months as we discover, oh, you know, this is a better metric than what we used before. Oh, those flame graphs are way cooler than we expected. And we keep getting more and more examples. So basically, these are the key things. We'll start with monitoring brokers, basic monitoring of clients, and advanced monitoring of clients. So world's fastest and shortest introduction to Apache Kafka. Basically, Apache Kafka is a cluster made of brokers. We have a bunch of different kinds of clients. We have producers and consumers. Producers write data to Kafka, consumers subscribe to topics and get events out of Kafka. We have stream processing apps, which are advanced combination of producer and consumer that can do advanced processing, like joins, windowing, analytics, these kind of things. And we have connectors. Someone here mentioned Kafka Connect. This is exactly the connector framework. If you need data from a database to Kafka, Kafka to Elastic, Kafka to S3, all these kind of things. In Kafka, data is written to topics. Topics are organized into have a set of partitions to them. So when you write into a partition, and you have full order guarantees inside the partition. Each event has its own offset inside its own partition. Usually you partition by keys. So keys, if you write events with the same customer ID in the key, all the events about the customer will show up in the same partition. You have guarantees that if a customer opened the bank account, put in some money, took some money out, put some money in, all the events will happen in order. It makes no sense to take money out of the bank account you did not open yet. So this is the Kafka guarantee for strong ordering. Now, we also don't like losing data at all. So each partition is replicated 3 times. Each each replica will live on a different physical, it used to be physical hardware. These days it lives on a container, inside a pod, on a virtual machine, an EC2, and somewhere below all that we have an actual broker. And then usually we have a lead replica. All the writes go to the leader. This is what gives you consistency and ordering guarantees. It used to be that all reads would be from the leader. No longer true. Starting with the latest version of Apache Kafka, you can fetch from follower, which means if you have a replica closer to you geographically, you can just read from that. Super important in the cloud because inter-zone and inter-region communication posts in the cloud are absolutely crazy. So this is the best tip. You just spent 5 minutes, and I'm sure I saved a bunch of you some money. So that was quickest introduction to Kafka. And now, how do we make sure? So we're running Apache Kafka as a service in Confluent Cloud. We have, I'm not allowed to say how many customers, but it's a lot of them running in. I'm not allowed to say how many brokers and clusters, but also lots of them. And so we have to be very efficient about our monitoring, trying to figure out what's wrong without turning our life miserable with tons of alerts. So we start with how do we monitor the Kafka cluster itself, which is the thing that when we run in the cloud, this is the thing that I'm responsible to keep up and running. And we found out that there's really one important question when monitoring Kafka. can your users actually use it? If a user is trying to produce an event, is that successful? If he's trying to consume, is that successful? You can choose gazillion metrics, and I'll talk a bit about what's important. But this is the one important thing. It doesn't matter what the rest of the metrics say. If your users cannot write and read, it doesn't matter, and nothing else matters. They will not pay us. Our SLA just has a problem. So the way we monitor that is we use something called a canary. And it's one of the things that sounds super simple, and 2 years later it's like, oh man, that's way harder than it looks. I spent a good portion of this morning resolving an unfortunate deadlock in a canary. It would hang while shutting down. So not a big deal, but really annoying. So we fixed that this morning. Anyway, the idea is that you create a special topic, and you create it in a special way, and you make sure that it has as many partitions as you have brokers, and that each broker has a lead for one of the partitions. So it requires a very customized create topic, but Kafka will support that. And it also requires a watcher. You have to watch if you added new brokers, you need to create another partition and place it correctly. And then what you do is you start producing. I say here every 15 seconds, but our latest version actually produces about 100 times per second. And basically you calculate what percentage of those writes were read successfully. And according to how your SLA is defined, you say I was available that portion of this minute. And you send alerts. So we send alerts if during a minute we had too many misses. And you try to do it, you place your canary as close as possible to the user, which means that if you have firewalls, load balancer, tralala, tralala, ELBs, whatever, as close as possible to the user. Otherwise, as you may guess, if the firewall goes down, Kafka is up, Kafka is perfect, you'll get no other alert, but your users cannot read and write. So it doesn't count that Kafka is up. So you have to monitor from the far side of the firewall, the far side of the load balancer, as far as possible is from the brokers themselves, so you can catch all those issues, because, hey, Kafka is up is not an excuse. Now, if you want to be super cool, you can also measure latency. When you consume from Kafka, there is a timestamp for when the event was produced. So you can actually say, hey, I now consumed an event that was produced in seconds ago. Hopefully 10 milliseconds ago. If it's more than 10 milliseconds, we start getting worried. Okay, so this is like the big high-level metric, but you still need some details around it, because if it goes wrong, it can be anything. It can be Kafka, your firewall, whatever. So you still want to know some more specific data. One of the questions you want to know is, are all my brokers up? And there's basically two ways to know that. Am I receiving metrics that I'm supposed to receive from the brokers, or something that goes onto the broker itself and does PS minus EF, checks that the process is there. Choose one, but you need to have something that checks whether or not the brokers are up. And then below that, the broker is up, that's nice, but can I read and write from every partition? Because, for example, if a partition doesn't have enough replicas, it could be unsafe to write to it. So you have metrics such as offline partitions, partitions that all 3 replicas for some reason are unreachable. Under replicated partitions, that's not a big deal. We used to recommend please monitor on, and that's like the most important metric used to be under replicated partition. And we found out that it's incredibly noisy. Every time you bounce a broker, every time AWS decided to take off a machine, like Kafka will rebalance, you'll get a new machine within like 10 seconds or so. We have all the automation, Kubernetes takes care of this for us. Okay, I forgot to mention, we are running Kafka in production on Kubernetes. So far so good, thank you very much. So yeah, basically if a broker goes down, if AWS kills one of our machines, we will get something new back with autoscale within a few seconds. But we can still get an alert, depending on how we want to get alerted within 4 seconds that something is down, we actually want to get alerted. So under replicated partitions was too noisy for us. We went with under min ISR, meaning that out of 3 replicas, 2 are not available. 1 is still up, but that's kind of scary. This doesn't happen very often. This is a real emergency when that happens. And obviously, we never ever get to offline partitions because we wake up when we still have only 1 left. And then you also want to monitor for resources. Workers need some things to be happy and healthy. You want to check bandwidth. Bandwidth is kind of can get tricky because you want to alert on percentage, but nobody ever knows how much bandwidth they actually have. I don't know, again, we are talking cloud, I'm buying a bunch of X5, R5 extra larges. Amazon tells me you have up to 1 gigabyte. Absolute total lie. We've never ever seen 1 gigabyte on any of those machines. Does not happen. We think we have up to 100 megabytes, but you know, that's how things are. So basically you need to do load tests. You need to understand what is the actual bandwidth that you have. It will not be the same going in and going out, because going in, you're writing a byte, it gets replicated to a few other machines, all three of them write to disk. You end up, you can actually have a lot more reads and writes on a given size of cluster. So make sure that you have two different limits on that. CPU is CPU, disk is disk, those are easy. And the thing is that what do you do when you run out of them? And I agree, we don't decouple them the way the Pulsar does, so you only have one machine, it has bandwidth, it has CPU, it has storage, it has everything. If you run out, you add more of them, like anyone else does. We use a data balancer. You have the Confluent Auto Data Balancer or Cruise Control, open source from LinkedIn. You run it, it has self-healing mode. It will just, whenever I add a broker, it will automatically move partitions over, so a few minutes later, the cluster is in good shape again. Okay, other important things to keep an eye on. Controllers. Kafka has a controller that is responsible for leader elections. You want one of them. If you have 0, it's bad. If you have 2, it's actually even worse. You want to make sure Kafka is in touch with Zookeeper. If you're seeing a lot of disconnects from Zookeeper, things are bad. All those things are very important. Network and request idle percentage being too low means that you are running out of threads. You may need more of them. Request time going up means that, hey, maybe users are unhappy. All those are important. Do not alert on them. Every time we tried alerting on them, we ended up waking up for something really stupid at a stupid hour. We used to do, if consume request time was above 10 milliseconds, we'd get an alert. It turns out that things are noisy. You sometimes have slightly more, and after a while you get alerted and you look, oh, actually everything looks fine, you go back to sleep. Third time you won't wake up anymore. So we basically, we are starting from, is anything painful from the user, and then looking down. Okay, the users are feeling pain, which one of those other metrics may explain what we're seeing? It seems much better for sanity. One thing we discovered that if we think that something is weird and we look at all the metrics, we will find something weird and we'll basically spend the next week kind of researching a very interesting things that happened in the cloud. Every time. So, and we actually had a case where my manager asked me, hey, you know, a customer had an issue on that cluster. Can you take a look what happened on this cluster at this time? And I looked at the wrong cluster, and I found actually very interesting issues to look into. I spent about 4 hours troubleshooting the wrong issue. Yeah, basically, it's things are noisy in general. Metrics can be very noisy. Clouds are very noisy. EBS disks are fast or slow, very much at random. So don't try to randomly chase down things because you will find them. So yeah, that's the biggest lesson probably. If something is going to page you, it has to be something that is A, important, like, oh, I'm glad I know that this happened. Yes, the customer is really in trouble. I have to wake up and save the day. And it has to be actionable. I know what to do. It can't be a research project to figure out what to do. Okay, that's for the brokers. But what if I tell you that everything is fine? The brokers are fine, everyone else on the cluster is seeing 10 milliseconds latency, and yet somehow you are unable to do your million events per second. What do you do then? Well, first of all, obviously you start running on Confluent Cloud, so you wouldn't have to wake up for your own brokers. But then the next thing you want to do is obviously look at the actual application. And there's a lot of things to look at, but in general, I mean, applications either consume or produce or both. It shouldn't be that hard, right? I mean, it has to be something very straightforward. So looking at the simplest possible application, consuming from a topic and writing to a topic, what can possibly go wrong? So first of all, the way most people would monitor their applications is by using consumer log. How many messages behind am I when reading from a topic? This is usually the calls we get. Hey, I'm seeing a growing lag. A high lag can be very momentarily, especially if you're doing like a million events per second, you can very quickly be thousands of messages behind. That's just like milliseconds of bleep on EBS or something. So you want to make sure to see a trend. Is the lag growing or shrinking or just kind of bouncing around? If you see the lag is growing, definitely you have to look into it because it just gets worse and worse. And this kind of thing you want to look into, so I'm just kind of showing it as a very simple example. And pretty much any kind of stream processing will kind of read from one topic, it will buffer some stuff in memory, it will do some processing, it then will send things to producer and it will write to a different topic, and then things will get act. That's basically how it works. What can be slow here? Well, pretty much everything, right? So it's possible that the producer is super busy and is kind of the bottleneck, or it's possible that the producer is actually doing absolutely nothing because the consumer is the bottleneck. The producer will have metrics like I/O ratio and I/O wait time, basically how much is actually spending on the CPU, how much time it is spending waiting on I/O, and if both of those are low, it's basically doing almost nothing. And outgoing byte rates, how fast is it writing? And if it's not writing fast enough, and you know it can write more, then possibly the problem is higher upstream. Those are all actual metrics that you can find on the producer. And then the two other metrics to look into is the batch size. If the maximum batch size, producers write to Kafka in batches, if the maximum batch size is very close to the average batch size, it means that you're all the time sending very full batches, which means that you could probably get a lot of performance by increasing your maximum batch size. Just write larger batches. It takes some more memory on the producer, but memory is usually cheaper than bandwidth. We have amazing compression on the producer, so larger batches are usually good if you need high throughput mechanisms. And then, of course, if you have a lot of errors, if you see high error rate, a lot of retries obviously don't come for free. They take time, so take a look at those. And then sometimes you have things on the way, you have threads that are waiting, you have a buffer pool wait time. This usually means that the producer is blocking someone upstream, especially the buffer pool wait time. It means that the producer's memory is full, it's selling as fast as it cannot accept anymore, and that's exactly when you want maybe more memory, maybe more CPU on the producer, etc. And then same thing, you want to look at the consumer. You have same metrics. Is it actually waiting a lot? Is it working as fast as it can and using all the CPU? What is the rate at which it's reading? Hopefully the rate it's reading and the rate you're writing are more or less the same. If there's a big gap, you're probably looking at memory up somewhere. And then the same way that we have batch sizes writing to Kafka, we have fetch sizes reading from Kafka. So you want to, if you see that you're always reading very large batches out of Kafka, you can just give the consumer a bit more memory, read even more. Again, those large batches, when you're looking for high throughput, those are your friends. So this is just very high-level metrics where you look at the dashboards and like, aha, I see the problem. The consumer has too small batches and therefore it doesn't get enough throughput, and therefore it slows down the producer. I found it. Sometimes, dare I say, even most of the time, the problem is not there. The problem is that someone wrote a really slow loop somewhere in your code, and we need to catch them. Oh, sorry. The record max lag, that's the client-side monitor for the consumer lag. You can monitor it on the broker, again, using something like Confluent Control Center, LinkedIn Barrow, there's a lot of tools for lag, or you can just monitor the consumer itself. It will tell you how far behind is it. But of course, those are just simple. Sometimes you want to dig really deeply and do advanced things. So,
thank you, Ren. So I'm going to talk a bit more about the bottom part of that chart that Gwen showed you, which is the stream processing applications. The first thing that I want to kind of talk about, oh yeah, is Gwen added a nice slide for me here. That was nice. So those are a bit more complex, and to understand those, sometimes it's not just enough to look at your metrics that you have. There's a lot of other things that may be going on if you're encountering any kind of problems. So the one thing that you can do in order to find out about this problem is to profile your applications. Why would you want to do that? Well, the first thing is that you really want to understand where those bottlenecks are. And if you take the example like Gwen gave you, the simple consume, process, and produce, you have to know where those things are happening. So the first thing is that metrics sometimes are hard to come by. I mean, most of the clients that we talk to, usually they barely have any metrics whatsoever. They usually have some metrics on the servers, the brokers that they're monitoring, but their own applications, go figure. They probably don't have anything, even though the clients have lots and lots of metrics. Most people actually don't even monitor those. That's not the first thing that they actually think about when they do that. The second thing is that they don't actually tell you the full picture. First, you have to know exactly what to look for, and most of the time, a metric only exists because someone else encountered the same that problem before. And in most cases, the problems you're going to encounter are things that no one else has encountered before, so you probably don't have a metric for it. And then the last thing is that you can do as much testing as you want. Most of the time, you will not see those issues in your development or staging environments. They will only happen in production. And by that time, it's probably too late to try to debug things. And the only recourse you'll have is to actually do this profiling in production directly on the machines that actually have critical customer data. And some of the interesting things that you find out from doing this kind of profiling, and some of those that we found out ourselves, is that you probably don't spend that much time in your own code. So when Gwen said oh, you have this expensive loop that's doing all this complex computation, I mean, yes, that happens. I mean, but usually you know when that's happening. And most of the time when you see bottlenecks, you're like, okay, well, this is something, pretty simple application, there shouldn't be any issues with this. And that's when you find out it's not actually in your code that it's happening. It might be somewhere else in your stream processing framework, in your network layer, you don't know. Those things you cannot really find out even if you had the metrics. So that's why it's important to have other tools to get access to that. One fun thing is that you find out if you start processing very high loads on the order of several million events per second, is that you're probably spending most of your time just deserializing, serializing your data. Even when you do very simple things, you probably spend 20% of your time doing the deserialization, and those are actually they're not trivial. Unless you already optimized your format to actually make that very cheap, most of the time that's not going to be the case. And as you build these streaming applications, you're going to have to manage state. You may be doing some aggregations, so you're going to have to see that your I/O is going to matter a lot more. Not just your disk I/O, but also your network I/O. A lot of things might be going on that you don't see at the high level. So my tool of choice for profiling is called Async Profiler. It can attach to any JVM-based application online, and you can start profiling this without impacting your production workload all that much. Really, the performance impact is minimal. And the nice thing is it actually works out of the box. You don't have to have any kind of special JVM flags. And you can run some kind of third-party container that has a JVM in it and just attach to it. And on top of also profiling the JVM itself, it will also profile your entire Linux kernel stack underneath. So you can actually really drill really deep into the entire stack and see what's actually going on. And like I said, it's low overhead, so you can actually run this in production very safely. That being said, there are other tools out there as well. They're just as good. I mean, if you look at Java Flight Recorder, which is now part of OpenJDK 11, it's open source. You can there's some very nice UIs like mission control to use to analyze the dumps from those tools. One thing that at least for our use case in terms of streaming applications is that it doesn't give you the insights into the native application stack. So it doesn't give you insight into the Linux kernel. It doesn't give you insight into all the C++ functions that you might be calling because you're using some native RocksDB or something like that. If you want to have insights into the end-to-end all the way down, you have to have something a bit different. But if you only care about the JVM part, and you're already running JDK 11, which unfortunately is not most of our customers, you can actually use something like Java Flight Recorder, and it'll give you a lot more insights into things like the garbage collection cycle and other things that you don't necessarily get with Async Profile. So pick the right tools for what you have, but the rest of the presentation will really focus on Async Profile because I think it's a great first tool to really go to bat with and try to find what's going on in your application. So Async Profile is actually pretty simple to install. So if you're like one of those old school folks that doesn't have containers, it just has like bare metal or some kind of EC2 instance you can SSH into, just clone the repo, hit make, maybe you'll need some of the C++ compiler, and you'll have your JVM installed. That's all you really need. And you can go ahead and start profiling, just passing the process ID. This will sample CPU for 30 seconds and just dump out a nice little chart for you to look at. So this is what one of those charts look like. So Brendan Gregg, who's now at Netflix, has kind of like popularized this, and he's the one who created the tools to make this a really cool feature. This chart is actually interactive, so you can actually click through and drill down and see what's actually going on. And but before we go a bit deeper, I think I want to explain a little bit what it is. So the first thing is that think about the x-axis as your CPU time. So what you can see at the bottom is like we have like this is 100% of your CPU, and then at the vertical axis, that's how deep it goes into a stack. So you can see the entire call stack of your application over this 30-second period. You can see all the functions that were called, where they came from. So at the bottom, you have basically the main function of the JVM, and then we'll have all the different, it goes deeper into the stack. Different calls represent different parts of the JVM or the code, and we'll go a bit into that. So the first thing is you can see on the left-hand side here, is all this yellow part here is actually the garbage collector. So this is basically what this tells you. It tells you all the functions that are being executed in the garbage collector, and basically it's telling us that we're roughly spending 20% of our time, CPU time, doing garbage collection. So that's something you'll probably see very often in stream processing applications. You're taking all these little messages, deserializing them, creating all these like very short-lived objects, and then throwing them away. If you're doing any kind of stateful processing, you may hang on to those like for several seconds, at which point they become a lot of garbage, and that's when those things can become pretty hard for the JVM to clean up, and you may have to do some garbage collection tuning. But this is something that can give you an idea of what's actually going on. And this particular example is actually from one of our big streaming applications we run at Confluent. So this is actually something we've used to debug and optimize some of the cases. And this is a stateful streaming application, so we'll get to see the full thing all the way from Java to JVM to native code. The second part is we're doing a bunch of aggregations in this code, and this is all the time we're spending in RocksDB doing these aggregations. So that's the kind of thing you would never really be able to see if you didn't have the full stack profiling into your native code. On the right-hand side, you can see the calls from the Java code, which is all the green part. That's your Java code. The yellow stuff is the native code in the JVM, and then it basically calls into RocksDB, and you can see there's a bunch of like seek operations that it's doing in RocksDB to look up some keys, and then maybe some puts and gets on the shorter ones. And on the far left side, what's going on is that you have some RocksDB code, but that's not actually being called by Java. And what this is actually this background compaction that happens in RocksDB. So we're actually spending a lot of time doing compaction, doing aggregations, doing like all these put and gets and updates and seeks in RocksDB. All of that is not time that you're actually spending in your application, that's in your code. This is all part of the time you're spending in the framework in order to do what you're trying to do. And this is where it can be, you can sometimes detect, like you might be doing stupid things in RocksDB, or maybe you can identify some bottlenecks in the framework that you're using. The last thing, before we go into your application code, is the Kafka call loop. So this is the time we actually trying to get data out of Kafka. We're deserializing it and then passing it on to the application. And what's left, this is the actual time that it spends in your code. So this is the time it takes to actually do some kind of like fancy computation to do these aggregations. You might be doing everything else is just a framework. So if you were to do any kind of metrics in your system, like you look at a bunch of metrics in your application, you probably would not find out all these different things from that. You can only see that by actually doing this profiling. So it's very important to spend where you spend your time. And the reason for that is that streaming applications are very complex beasts. The way I like to think about streaming applications is really trying to divvy up the time you're spending fetching the data, including deserializing it, the time you're processing the data, and the time you're spending sending the data. And going back to Glenn's example, like those are the three things that you're really trying to understand in order to optimize your application. Most of the time, CPU and CPU usage on those, they're very poor capacity utilization metrics. It doesn't tell you if you're blocked on anything or anywhere. All those things are, I mean, they're useful, of course, but in a world where you have hyper-threading and containers, usually you're never going to exceed anything beyond 65% CPU anyways. And it doesn't tell you what's blocking. Are you slow because you start fetching the data? Are you slow because you start processing the data? Is there something downstream or upstream that's impacting you? You wouldn't know that. So one good way to find out is to actually calculate the ratio of wall clock time you're spending in those things, and that can help you identify where the things are happening. So if you sum all the wall clock time you're spending in all those things, and you come up to 100% of the wall clock time that has elapsed, then that means you have a very good capacity utilization. You're actually making very good use of your time. If you sum up all this time, you're only spending 50% of your wall clock time doing anything, and the rest is not accounted for, that means you have bottlenecks elsewhere, and you can identify that by doing some more profiling. One nice thing is of doing this kind of work is that you can detect a lot of unexpected side effects. So this is an example of a streams application where we actually saw all these very expensive cache flushes, and they were causing a lot of seeks in RockCP. And it's something that we didn't actually see in our testing, and only surfaced in production. And it's one of those like very tortuous code paths in your application that you don't really that are completely non-obvious to detect. But basically, when this cache was getting flushed, it was causing a bunch of seeks in RockCP, which are very expensive, and it was not. It was something that's very difficult to find out. You would have never guessed it from actually looking at the code without digging really deep. And we were spending roughly 23% of the time just doing those cache flushes, and which was causing things to get extremely slow. And just to understand what the cache is used for, is if you're writing a cache for Streams app, oftentimes when you're doing any kind of stateful processing, it doesn't make sense to send any updates to, let's say, an aggregate value downstream with every single computation, right? So you want to wait a little bit of time before you actually send it down. So there's a cache that maintains the state, and after a while, we're like, okay, well, we processed maybe like 30 seconds worth of data, or we've processed a certain number of bytes, and we'll send an update downstream so that any microservice or other application that uses that data can get an update. But we don't need to send an update with every single message, especially if you're doing things, if you're processing millions of events per second. We don't want to send an update for the aggregate value every time we get a new message. That would just be way too expensive. So after we found out like this very tortuous code path that was getting executed, we were actually able to get it down to 5% of the time by replacing some of those seeks with very simple guess inputs and optimize a lot of the Kafka Streams framework. So yeah, just to summarize, we had these very inefficient cache flows that we're calling inefficient methods in RockCP. Those things were never problems in testing, and only the production workload really caused this to become a problem. And the reason is that in production, we suddenly had all these different keys that were getting up at the same time, and those were causing the cache to fill up instantly and always be flushing. So with every single message now it's flushing and causing these expensive calls, which is something that we didn't really see until we actually did the profound. And by simply increasing the cache size in production, we're able to get things in order of magnitude faster. I think it helps understand I/O bottlenecks. So this is an example of just a very simple part of a Kafka. I think it's a producer. We send the data. This is actually like all the stuff that happens all the way down into the kernel code. And one of the interesting things about this is when we use SSL to write data. You can see all the red part is all the time we spend in actual kernel code. First part is like how much time we actually spend writing to the socket, and the first half is how much time we actually spend generating random data. So if you ever like work with Kafka and SSL or like other applications, you need to have enough entropy in the system to generate random numbers, because that's how SSL works. You need a bunch of randomness to make things secure. Well, you're probably spending as much time generating this randomness as you are actually writing to the socket. So don't be surprised that your performance drops when you're actually using SSL. What you can see here, like this yellow part, on the orange part on the left-hand side, that's just the read from their view random. That's how it is. The next thing, so beyond the CPU profiling, one nice thing about async profile is you can do things like per-thread profiling. Stream applications are often complex beasts. You have very heterogeneous workloads. You may be running very different functions or threads that do very different things in the same JVM. It's common among most of those processing frameworks. So sometimes it's very hard to understand what's actually going on or which task might be the bottleneck because you have a bunch of very different things happening in the same process. So if you break it out by thread, that can give you an idea of what's actually happening and where the problem might be. Or if you have any kind of imbalance in assignment of the different tasks or different threads or different partitions, depending on how you divvy up your workload. So once you do that, you basically have this playing graph nicely broken down, and you can see the portion of each time doing CPU time spent at each thread. In this case, we have roughly like a very equal distribution, which tells us that we have a very well balanced process. But if you have some like wild differences between all the different threads, and you can see the process ID at the bottom, you can tell if there's a big discrepancy here. The nice thing about async profile doesn't just do CPU profiling, is it also tells us when you're not spending time on your CPU, when you spend time waiting. So just by adding these extra little command arguments, you can now tell it, hey, tell me how much time I'm actually waiting on different logs. And now instead of looking at your chart in terms of how much time you spend on your CPU, this is how much time you actually spend waiting. So this is interesting, like some of the things that you might see in a Kafka consumer application. We're basically here seeing that we're waiting 130 milliseconds over this period of time on this consumer coordinator object. So it actually tells you exactly which log object you're waiting on, which is very useful when you want to debug some application, and you know exactly how you got to wait to that log wait in the stack. So it's extremely helpful to understand those bottlenecks. And the other thing we're waiting on is we're waiting on metrics initializations. So this is actually doing startup. So what we can see is that there's a whole bunch of rebalancing happening, which is why we have this consumer coordinator log that we're waiting on a lot. This indicates that our application is probably doing a lot of rebalancing. And on the other side, we're doing a bunch of initialization of lots and lots of metrics. The Kafka client have a lot of metrics, and we initialize those. They all kind of are fighting for the same blocks. So you're basically spending a quarter of a second out of those 30 seconds just waiting on those blocks. So you can probably optimize that a little bit to increase startup time. But if you're doing this on a running application, then you probably have bigger issues. Those kind of profiling have helped us detect a lot of timing bugs like we had, or lock contention issues. So sometimes we had these consumers that were calling poll in a critical loop, and it was basically waiting on new data coming in while it was doing some other while it was restoring the actual application state. And that works fine as long as data is coming in. You never have to wait on poll. But if suddenly you don't have data coming in anymore, then your poll is just blocking for a few hundred milliseconds, and you basically the whole state story grinds to a halt. So again, things that you don't see very often when you're doing testing, because when testing you have some data flowing, and it's always when things go bad that those kind of bugs creep up. And by just fixing this little poll issue, we were able to get state restoration from minutes to seconds in our Kafka streams app. Last thing I want to talk about is the allocation profiling. The nice thing about this feature is that now, other than just looking at CPU time or log contention time, you can look at how much memory you're allocating where in your code. So this is very powerful to try to identify any kind of memory leaks, or if you're seeing any garbage collection that's causing issues. It can help you understand where that's actually happening and what part of your code is allocated the most memory, without having to go and look at a bunch of heap dumps, which becomes increasingly infeasible when you have 32 gigs of heap and you try to load that on your laptop. Usually doesn't work too well. So this is, again, the Kafka client that we've done some allocation profiling. All these blue bars tell you what kind of objects are getting allocated. In this case, we can see there's a bunch of byte arrays and byte profiles getting allocated. And this is doing the actual copying of data within that client. So there's a lot of like intermediate byte arrays getting created. So maybe this is a sign that we could optimize this. And again, this is really helpful to try to understand what's causing your memory usage in your application. And since you don't have to wait for a heap dump. A heap dump is just like the end state. Here you can actually profile the live application and see over the course of like 5 seconds why was running what actually got allocated and where the extra memory came from. So why is this useful? I mean, again, like I said, it helps reduce GC pressures if you have a lot of long-lived objects. Large byte arrays can be very expensive to initialize. Sometimes you do that during serialization and deserialization, especially if you have compression, decompression happening. You have to allocate all the intermediate byte arrays. We've been able to improve performance by orders of magnitude by identifying some cases where we were able to reuse maybe some byte arrays, like we have building some buffer pools or byte array pools, as opposed to creating new ones every single time. Now it's not always possible, but those are the kind of like things that it can help you identify when you're allocating 64 kilobytes at once. That takes a long time, and if you're doing that with every single batch of messages coming in, that can become quite expensive. And that helps you identify those things. So I'm going to stop here. I think the one thing that I want to leave to end there, there's a bunch of slides, and we'll post them on the meetup on how to do this in container applications. That's where it gets a little bit more tricky, because in order to do profiling, you need to have certain privilege on the system. You need to attach to the JVM process. So if your JVM process runs in some container and you're in a different container, or you're on the host machine, if you're lucky, you have to go through some hoops to kind of get your agent attached to that. So there's a bunch of instructions here that kind of help you go through that. And the most convoluted case, for better or worse, is on Google Cloud when you're running Google Kubernetes engine. You don't have access to anything pretty much, because your home is mounted non-executable, so you can't even like run anything out of there. Everything has to be in a container, and you can't install any packages. So if you need anything extra on that machine, you have to basically hop into this toolbox container and install like your stuff there, and then you can actually do your profiling out of that. But you have to go through these hoops, like sometimes going back to the host to figure out where your container is and copy the agent library into the container before you can actually do that. So I'm not going to bore you with all the like step-by-step instructions to do that, but this is basically what you have to follow and do in order to be able to do this in GKE. Plus, you may have to turn on some special kernel flags so that you can do this outside from within a container, because the kernel by default now doesn't allow you to do a lot of those things. So you have to actually allow your container to do the perf event profiling so you can get access to those kernel level traces. Otherwise, you'll just see a bunch of unknowns in your stacks, and that's not very helpful. So you want to actually get the privilege to do those kind of things. And then the funny thing is that when you actually run your profiling and you output a file, because your agent ran in the target container, the file gets output in the target container, not in the container where you ran. So you have to then go through some hoops and copy the file back out of the container where the application ran. So I'll leave it as an exercise to you guys to do this at home. You can probably figure out how to make this work inside of some kind of like special profiling container, and automatically set all the right things, and maybe create some fancy volume mounts where you can dump the flame graphs into, so that you can do this with a click of a button, as opposed to having to go through this laundry list of steps. But at least it's good to go through it once yourself to really understand what's going on. And yeah, so go ahead, try it out. There's a bunch of resources on GitHub, Confluent blog, things like this.
Yeah, you have to leave the discount on so people
yeah,
can
so
go to
anyway, so we have a community Slack where you can also ask us any questions about anything really. And yeah, we just want to thank you from Gwen and I. And for that, we also want to give you 25% off Coffee Summit in end of September. I think it's September 30th and October 1st in San Francisco. So if you use this code, you'll get discounts.
Thank you.
Thank you.
Oh, and I'm speaking in Kafka Summit about how to do upgrades seamlessly in the cloud, zero downtime. So if you're into this kind of stuff.
Yeah, thank you, Xavier, and thank you, Quinn. So I didn't get a proper introduction at the beginning. And Quinn is the longtime Kafka contributor and she's author of the deputy guide for Kafka, and Xavier is the first employee of Confluent. Yeah.
One of the first.
One of the first.
No, one of the first is like one of the first 100 now. It's like
So assume that we can get the slides later
Yes.
and
Yeah.
and post. I can share with on the meetup.com. And the same thing for the first presentation. So any questions?
So can you talk a little bit about the overhead of your own profiling scheme, and do you guys do any sampling?
Yeah, so typically the overhead is fairly noticeable. I mean, all this happens so when you do the profiling or the JVM sampling, those happen at a certain frequency, and you can change the frequency if you'd like to. But typically with the defaults, you're not going to see any impact on the application. And it doesn't require any kind of instrumentation of the bytecode or anything. It really just like effectively takes a snapshot of the stack at a given point in time, and it doesn't impact any of the like JVM save points or anything. It doesn't depend on any of that. So you're not actually slowing down the application or causing any kind of de-optimizations in the JVM. So that's very important to understand, because otherwise, if you have a bunch of inline methods, you want that to stay that way in order to be able to identify it. But it actually is able to preserve a lot of the stack information that you wouldn't otherwise be able to see, because it actually talks to the JVM and uses methods that have been available in JVM since JDK 7 in order to do that.
What about the first part? The first part you talked about, do you do any sampling there? Like the first part of all the other metrics you're collecting?
So the rest of the metrics are part of Apache Kafka.
Yeah.
They are there whether you want them to be there or not. I'd say that the main thing to be worried about, the default way to collect them is via JMX. JMX has this RMI global log. If you have tons and tons of metrics, you maybe want to make sure that you're not collecting all of them at once, to kind of make sure that you're not holding the log, especially if you hold the log for 2 minutes and try to collect the data every 30 seconds, it can become a problem. We ran into some problem with that, so just basically make sure that your Datadog agent or Prometheus scraper or whatever it is that you have collecting metrics only collects the metrics you need and can do it in a reasonable amount of time. And you can use flame graphs to discover if things go wrong. I think that's how we originally discovered that we have a problem with our metrics collection, is that we've seen basically tons of thread blocking on the RMI log.
Any other questions? So I got a question. So now I see two presentations. One is Kafka, one is Posa. In some features, they are overlapping each other. As you know, I've never seen Posa before. This is the first time I see the presentation. So can you comment on the pro, from your perspective, with the other product? I guess it's a question for each other. You go first, and I'll ask in a second.
I think it's mostly up to the users to judge. I mean, we are engineers, I think all of us here. Building systems involve trade-offs. You make specific trade-offs with what you think are good optimizations and optimizing for maintainability, for ease of use, for performance. You do all those things, you think you did a fairly good job. We try to improve every release, add more features, add more capabilities. We definitely got inspired by some of Pulsar ideas to make Kafka better, so we definitely appreciate having someone to copy features from. But yeah, at the end of the day, you look at both systems and you say, those are the trade-offs that I'm comfortable with, and those are trade-offs that I'm not.
Yeah. One of you want to answer the question?
Yeah, so obviously there's a huge overlap in terms of use cases that we target and we support since the beginning, but there was also a very big differences in the design and the architecture, and what was the initial target. So Kafka was coming from a use case that was like a log collection, data processing. In our case, we came more to database replication and online queuing and the transactional capacity part. So we had like or like a multi-tenancy since the beginning. So we had like things like durability was and replications were things that were ingrained there, and things like durable replication, again, like all these kind of things were there because that was the original design of the system. And then from this design, also like you can convert into one thing, but the original decision that you made, you cannot change that at any point.
Thank you very much for both. Any other questions? No? Okay, thank you so much. Appreciate it.